Thank you very much for the introduction, and I would like to thank the organizer for giving me an opportunity to talk here. So I will try to, in certain sense, to cover some work of Vietnamese colleague and UK colleague in Mexico. And Andre will talk a little bit more about. I expect some continuation of my talk. So one of the main objects in number theory is the study of zeta function. So most of them comes back to the Riemann zeta function. So Riemann zeta function is a function of one complex variable given by the formulas. So we take the s to be a complex number. And we define zeta of x to be the sum of 1 over n to the power of x to the power of s. So you have an infinite sum here. And we define zeta of s to be this sum. And to ensure the conversions, we have this condition. And then is an exercise to show that it can be extended to a meromorphic function over the whole complex plane, and with only simple pole at s equal to 1. And then people try to do something more general for any number field k, which I mean a finite extension of Q. We can define the Dedekind zeta function, and this is an extension. So some fundamental properties of the Riemann zeta function. So in number theory, we love a lot to study primes. So the first property is that we have an Euler product. So the zeta function can be written as a product over prime p of what we call local factor. So the second property is a kind of functional equation. So it says that the Riemann zeta function satisfies a functional equation relating the value at s and the value of 1 minus s via gamma factor. So you have a kind of symmetry between 1 minus s and s here, whereas the gamma function is defined by a very simple expression. So the third one is a result discovered by Euler long time ago, which says that if you take k any positive integer, then zeta 2 of k is a product of a rational number times a suitable factor of pi. And the last one is a very famous one, the Riemann hypothesis, which says that if you look at the non-trivial zero on the critical strip, then it's all the non-trivial zero lies lie on the critical line. The real part of s is 1/2. So this is the fundamental properties of the Riemann zeta function, which we would like to study for other zeta function or L functions. So now one important problem in analytic number theory is to understand what we call the moment of the Riemann zeta function. So it's given by this expression, is integral from 0 to t of zeta of 1/2 plus it to the power of 2k. So for a positive real number k, it's conjectured that the moment is equivalent to a constant c dependent on k times t times a factor of log t. So there is a precise conjectural value of ck due to Keating and Snaith. And up to now, this moment well understood when k equal to 1 by the work of Hardy and Littlewood, and k to 2 by the work of Bingham. And for lower bound, there were important work of Hitchbrow and Ramachandra assuming Riemann hypothesis, and upper bound by Sean Dararajan assuming Riemann hypothesis. And here we have two Vietnamese colleagues who are studying this kind of problem. So Bùi Minh Hung from Manchester studies not really positive moments, but negative moments of Riemann zeta function, and recently he obtained some asymptotic formulas in certain ranges of zeta of S. And Ngo Chung Hiếu studies some relative question for central values of other kind of L functions. So then, as I said before, there are many generalization of this kind of the zeta function. So I have talked about the Dedekind zeta function. Another important kind of zeta function is a zeta function of elliptic curves. So this is a mathematical definition of elliptic curves. So it is a smooth projective curve of genus 1 over a field K with a distinguished point. But we will see very soon that it's very simple. So if we take K equal to Q, the field of rational numbers, and then every elliptic curve E can be defined by the Weierstrass equation. So it's very simple. You have E squared is given by H cubed plus AX plus B, with A and B rational numbers with a technical condition that the delta expressed in terms of A and B is different from 0. So this kind of technical condition is just to get something smooth. So why elliptic curves is so fascinating for number theories? Because we have a group law on this curve. So here you have the elliptic curve. So the group law, you take 2 points P and Q. So because you have something cubic, so if we go through another point and you take the opposite of this point to define the sum. So you have a group law on elliptic curves. And now to define zeta function, we need to take any prime and you distinguish between what is good and what is bad. So we said that it's good if you take the reduction mode P, you still get an elliptic curve. And because you are over a finite field, so you can count the number of points. So here you count the number of points over FP. So it's a finite number. And you define AP to be P plus 1 minus this number. And it's known by heart. So you have an upper bound of AP. And for the other P you call is bad. So you just put AP equal to 0, 1, minus 1 as you want. And then the zeta function defined by something similar, but now we take, by definition, we take just the product of local product. So you have some local factor for bad 1 and some local factor for good 1. But what we need to remember is just we define by the inverse process. So we define by a product of local factors. So here is one of the most famous theorem in during the last decades. So it's called the resolution of Shimura-Tanayama conjecture due to Weiss, Taylor Weiss, and the work of Taylor, Conrad, what is his name? Gray. So which says that every elliptic curve over Q is modular. So one of the consequences of this is that this L function is an L function of a modular form. So it has an analytic continuation to the complex plane and satisfy a functional equation. And then people trying to generalize this the modularity theorem. So we have the work of Freitas, Lê Hùng Việt Bao, and Zigzag, which proves that every elliptic curve E now not over Q, but over a real quadratic field is modular. And then recently, for many imaginary quadratic field, here you have something real, here you have something imaginary. There is a work of Craiani and Newton, who proves that every elliptic curve E over K is modular. So this kind of theorem, special cases of a more general conjectures formulated by Langlands. So it's known as under the name the Langlands program. So in developing this program, Langlands conjectures a series of identities called the fundamental lemma, which proved by Bao using Hitchin vibrations over curves. So in this in the number theory section, we will heard about some variants of the Hitchin vibration by Bao and Đỗ Việt Cương from Vietnam. So the next one of the related topic to the zeta function over zeta function of elliptic curves over Q, so-called the modern conjecture. So let E to be an elliptic curve defined over Q. Then we have seen that the set E of Q is a group. So this group is finitely generated, a billion group, and the rank E of E is defined to be the rank of E of Q. And then there is another famous conjecture due to Birch and Schoenenberg, which states that if you look at this analytic function, the L function of the elliptic curve, then the vanishing order of this function at S equal to 1 equal to the rank of E. So it's a kind of a bridge between some analytic objects and an algebraic objects. And later, the Birch and Schoenenberg formulated a precise formula for the leading term of L of E of S in terms of several quantities attached to the elliptic curve of E. So then people people can ask what happens if we look at any curve of genus greater than 1. So this is the original modern conjecture and proof finally by Fanting, which states that if you take C to be any smooth curve of genus greater than 1, then C of Q is finite. And this is not the end of the story, but this conjecture has evolved into important conjectures in Diophantine geometry. So in this order, you have modern long conjecture, Andre Ott conjecture, Simberping conjecture. So I expect you will heard more about in the talk of Andre after that. So this kind of conjecture are very important, and they are related to the model theory that some people here working on. So, and now I would like to talk a little bit about what I'm working on. So it concerns the transcendence of zeta values. So by the work of Lindemann, we know that pi is a transcendental number. This means that if you take any polynomial of rational coefficient, then p of pi is different from 0. So we know that if we take the even value of the zeta function, this one is a rational number times a power of pi. So by Euler, we know plus Lindemann, we know that this number is transcendental. And then there is a fourth law conjecture which says that if you look at the number pi, zeta of 3, zeta of 5, then they're supposed to be algebraic independent over Q. So this is all what we know about the nature of this number. So it's known by Aperi in that zeta 3 is not irrational. It's not then by Ball and Rivoan that if you look at the Q vector space spanned by zeta 3, zeta 5, then it's infinite dimensional, but we don't know whether or not zeta 5 is irrational or zeta 3 or is transcendental. So now people try is often happen in people try to enlarge a little bit the set of objects. So they define the multiple zeta values by not only taking the zeta value, but we put many variable k1 to kr and study this kind of the sum. And these values have been studied, turn out to be in many different branches in mathematics and as well as in physics. So you can see in the setting of Witten zeta function, Feynman integrals, and of course in mathematics in theory of mixed state motifs. So when r equal to 1, we recover the special value of Riemann zeta function. So I would like to present two most important conjecture in this theory. So we define a Fibonacci-like sequence of integers dk given by this formula. So you have d0 equal to 1, d1 equal to 0, d2 equal to 1, and you define recursively the sequence dk. And Zagier conjectures that if you look at zk denotes the Q vector space spanned by all the MCV of weight k, then the dimension of Z of k is dk. So you have a vector space spanned by all MCV, and Zagier he predicted the dimension of this vector space. And then Hoffman refined this conjecture by giving an explicit basis of this vector space. So it says that if you look at the MCV of this guide n1 to nr with ni just 2 and 3, so you have 2, 3, 3, 2, 3, but you just have the entry is 2 and 3, then it gives you a basis of this vector space. And the first half of this conjecture have been completely solved. So what does it mean? It means that we would like to have something like an equality here and a basis here. So the first half, I mean, you have the upper bound. So for all k in n, we have the dimension of C of k is less than dk. So this is exactly the optimal bound. So this is by Terrasoma, Delin, and Kocherov. And then Brown, he proved that in fact, Z of k is spanned by MCV, given by exactly in the conjecture of Hoffman. So Francis Brown, in fact, the second part is much more important. It says that we need only to know the dimension of Z of k, and it implies a very strong result. The conjectures that I talked before. So you have pi, zeta 3, zeta 5, algebraically independent over Q. So this is quite stunning because you just need to know the dimension of something to imply these guys that you don't have any relation among this number. So this is done by Francis Brown in 2012. And after that, there are many work trying to so here you have just the upper bound, and you have the a generating set. But the bad news is that the second half is completely open. By this, I mean that we don't even know any single case such that the dimension of Z of k is greater than 1. So we still have something to go from here to here because you need to prove the lower bound in certain sets. And I just mentioned some of my work with two Vietnamese colleagues, Yuan and Hương. So we prove an analog of this conjecture is a function field set. So this is all I would like to talk about the number field. So there is a branch of mathematics I don't mention in my talk. It's about people working on periodic integration and motivate integration related to the talk of Andre. So Andre is a more competent than me to talk about this subject. So thank you very much for your attention.
Level 1 question, Tuan.
I have a question similar to the second part in there. So if you take a family of L functions, do we believe that the L functions, say a tree, are linearly independent of a Q, something like that? We take only one point, like we take over the family of L functions. Do we believe them to be linearly independent?
The trouble is that even for zeta, special zeta values, we don't know much about the nature of this number. So I don't think there are much of work working on this direction, because even for zeta values, we stop just here. So this is the point. So you can,
I mean, like at least for zeta of 3, we know that it is irrational.
Yeah, for example, for the generating part for theorem 1, there are work of the linear working on more general setting. But for the lower bound, I don't think we have any result at all. It's a very tough problem in Diophantine geometry.
Okay, thank you, Tuan. The next speaker is Andre Jaffe from UCL.